The question that I have is, what is Coulomb's friction law? Recall that in another video we talked about the causes of friction, right? We saw that the origin of friction includes molecular adhesion, surface roughness, and deformation, right? While this fundamental knowledge is necessary in dealing with friction in an intelligent way, we need a more practical method to model friction in our analyses. So this is where Coulomb's friction law comes in. So let's talk about it. Supposing, say, we do an experiment in the lab where we place a block on the surface and pull it sideways with the force P. Say the vertical force pushing the block down towards the surface is W. So this vertical force could be in the form of the weight of the block itself or an externally applied vertical force or a combination of the two. As we keep increasing the horizontal force P, gradually we know there's going to be a frictional force developing to resist that, right? So let's call the frictional force as F. As long as the block stays static, we know there's no acceleration to the block, right? And therefore the horizontal forces should balance each other according to Newton's law, right? So in other words, this P here must be equal to F. Let's also say we are going to keep measuring the horizontal deformation of the block relative to the horizontal flat surface. Just because the block doesn't have a motion doesn't mean there is no relative displacement between the two. In fact, there is going to be a relative displacement delta. And obviously this delta is going to be very small. So if you actually want to do this experiment, you need to have a highly sensitive horizontal displacement transducer to pick up this deformation accurately. So we did all that and we're going to plot F versus delta. You're going to see something like this. Alright, so it's going to be a rising type of curve and eventually it's going to become horizontal. It's going to taper off. So on this flat part we have the maximum value of F. F cannot increase anymore. So once P, the horizontal force that you're applying to the block, reaches this value, the block is going to start sliding. The vertical force equilibrium says that the reaction, the normal reaction between the block and the surface N must be equal to W, right? So in this experiment, we are not changing N, we are keeping W constant, right? And therefore N remains the same, but we are increasing P and thereby increasing F. It turns out that if you repeat this experiment with different values of W and therefore different values of N and measure the corresponding F, right, for each value of N, plot a relationship between Fm and N, you're going to see something like this. You're going to see a linear relationship between the two. In view of the microscopic origin of friction, which includes molecular adhesion and surface roughness and all that, this result seems kind of surprising, right? But it is true. It is surprisingly, very accurately true. So here we are not looking at all these microscopic regions, right? We're just plotting the macroscopically measurable force F against the macroscopically measurable N. So this is a macro model, a macroscopic model. This straight line can be represented by this equation where mu is the coefficient of friction. And this model is what is called Coulomb's model. So at the point of sliding, if you come back and look at the forces acting at the bottom of the block, we have N going vertically up, right? And Fm, the maximum value of F, acting horizontally in that direction, right? Supposing, say, I complete this parallelogram and define the resultant between the two forces, right? So this will be the resultant between the two forces. And this angle here, right here, phi, is what is called the friction angle. The tan of the friction angle is basically this divided by this, but this is equal to Fm, right? And therefore tan phi equals Fm over N. But from this equation, what is Fm over N? Fm over N is mu, right? And therefore mu equals tan phi. So once again, mu is called the coefficient of friction, phi is called the friction angle. but both represents the same thing. It represents the friction of the contact surface, right? Two different ways to represent the friction. As an example, the coefficient of friction mu of a brass-steel interface is 0.51, which corresponds to a friction angle of 27 degrees. So one side of the contact surface we have one material, the other side we have another material. The combination of the two materials will dictate the value of the coefficient of friction. Different combinations will have different values for the coefficient of friction. So it turns out that the Coulomb's model is not necessarily obeyed by all materials. For example, if you take cohesive soil, right, like a clay soil, this is the model that seems to capture its behavior. Here's a graphical depiction of the Coulomb's model, but here is a graphical representation of this equation. This model is called Coulomb's model. The relationship between Fm and n is still approximated as a straight line, but the straight line this time has an intercept, Fc. Coulomb's model does not have that intercept. In other words, the straight line passes through 0. So basically what we are saying here is that the resistance offered by something like a cohesive soil has two parts to it, a cohesive part and a frictional part. This cohesive part is independent of the normal force N. In other words, even if you don't have any normal force N, there's still going to be a certain amount of resistance, and that is exactly equal to the cohesive part. We know clay soils are sticky, right? It's like a sticky material. So that stickiness is the one that is responsible for this cohesive part Fc. The slope of this line here on Coulomb's model is mu, right? And similarly, the slope of this line on the Coulomb's model is also mu. Now let's briefly talk about the difference between the static friction and the kinetic friction. Remember in an earlier slide I said the relationship between F and delta is something like this, right? This is a sort of a crude representation of F versus delta. Here is an accurate representation of F versus delta for most materials. Initially, F increases with delta like in this first part of the curve. It reaches a maximum around here. Let's call that as F1. At this point, the block is going to start sliding. So somewhere here, the block is actually in motion. It's moving. Now, if you continue to measure F while the block is in motion, you're going to find that F is going to drop a little bit. All right? It does remain constant after that, but this value right here, F2, is smaller than F1, the value at the peak right here. So what's the difference between the two values? Well, F1 is the value while the block is still static, stationary, right? And F2 is the value while the block is in motion. And if I use F1 to define my coefficient of friction is going to be F1 over N, right? And that coefficient of friction is what is called the static friction coefficient. Whereas if I use F2 in my definition, and that is called the kinetic friction coefficient. And these are the most common notations for these coefficients of friction. Mu of S for static friction coefficient and mu of K for kinetic coefficient of friction. So here are some typical numbers. If mu S is, let's say, 0.5, mu K could be something like 0.4 or maybe 0.45 or maybe 0.35. So what exactly are we going to talk about in this course? Well, our coverage here is going to be limited to dry friction. It's going to be limited to sliding friction. In other words, not including rolling friction. It's going to be limited to frictional force obeying Coulomb's friction. In other words, we are not going to consider Coulomb's model or any other nonlinear model. Our problems may involve these mechanisms, sliding, tipping, and rolling. But if the mechanism is going to involve rolling, we're going to neglect the rolling friction.